Okay guys, so I'm going to go through this pretty quickly. All of this should be review. So what you should be doing is checking your work. If you get something wrong, listening to my explanations to understand why you got it wrong. But ultimately, if you're getting stuff really, really wrong and you're not getting it, you need to come in or email me. Once you've completed this, you're not 100% in the clear. That doesn't mean you understand everything because chapter 12 is missing from this, what we just did. So what I would highly recommend, go back, look at your old tests, which means pick up your corrected tests from my classroom and review those as well, because I will grab multiple choice from old tests. Okay, so I'm going to start with the first one, with the first question. The gas law that's used here is Charles' law, and the way that I know that, I'm dealing with volume and temperature, but I'm not dealing with pressure. Pressure is staying constant. So as a result, I'm using Charles' law, okay, which is V1 over T1 equals V2 over T2. The thing you need to remember is that you cannot be in Celsius. You need to convert to Kelvin, and so that's what I did here. I added 273 plus this 250 and got 523. Everything else is given to you. You're trying to solve for T2. So what you need to do, you do 130 times T2 equals this times this. And then you end up dividing both sides by 130, and your answer is going to be about this. Okay, now I need to round. What you'll notice, I've got 2 sig figs here, 3 here, 2 here. So my answer needs 2 sig figs. So my answer is 340 Kelvin. Notice it's Kelvin. You don't have to convert back to Celsius unless I ask you to. Okay, so don't make more work for yourself than is necessary. The next question, we're dealing with pressure, we're dealing with volume, but we're not dealing with temperature. So temperature is staying constant, and I'm using Boyle's law, which is P1 V1 equals P2 V2. So here's my P1, one atmosphere. Here's my V1, which is 350 mils, which you can keep as 315 mils. That's fine. It doesn't need to be in liters. 0.775 atmospheres, and I'm solving for V2. So you divide both sides by the 0.775, and I get 406. The important thing to remember now, since this was in mils, the 315, my answer needs to be in milliliters. So be careful with units, be careful with rounding. This is 3 sig figs, because everything else had 3 sig figs, because otherwise I'll have to take off, which I don't want to do. And number 3, things that are given to you include volume, pressure, and temperature. Okay. A lot of people freaked out about the 3 kilometers. It's just giving you more information than you need, so just ignore it. Okay? Don't freak out. Nothing's staying constant in this case, so it's a combined gas law. It's P1 V1 over T1 equals P2 V2 over T2. This is my V1, sorry, this is my P1, and this is my T1. Now, notice I'm getting my T1 from, it tells me I'm at 20 degrees Celsius, so I've got to convert it to Kelvin. So add 273 plus that 20 degrees. Okay, here, same thing, I'm just plugging in my values. What you then need to do, you'll take 1.8 times this times that equals this times this times this. Okay, that's just, it's cross multiplying. Then what you'll end up doing to solve for V2, divide both sides by whatever you get when you multiply 293 and 0.667. Hold on one second. So divide both sides by the product of 293 and 0.667, and you'll get 2.42 because you wanted 3 sig figs. All right, next one. This is just a nice review of all of them. Here's Boyle's law, which will be given to you on your cheat sheet. What stays constant? Your temperature. Charles' law, what stays constant? Your pressure. Gay-Lussac's law, what stays constant? Your volume. And then combined gas law, nothing stays constant. All right. 5, it is not safe to put aerosol, blah, blah, blah. So in this problem, guys, I'm giving you volume, I'm giving you number of moles, and I'm giving you temperature. So as soon as you see all of those, nothing's changing. It's just asking you to find the pressure. You should be using your ideal gas law. Now, if you notice your R, the units for R are liters, atmospheres, Kelvin, and moles. So that tells you your volume needs to be in liters, pressure in atmospheres, temperature in Kelvin, and moles, well, moles. So here, pressure times, you're given 1 liter, which is great for your volume. You're given 2 moles, which is great. There's your R value. And then notice my temperature has to be in Kelvin, so I've got to add the 1,400 and 273 to get this. Okay? And then your answer should be 274. It should only have 2 sig figs because this is supposed to be 2.0 moles, so I get 270 atmospheres. This problem 6 is the exact same thing, except you don't actually have to convert because I gave you all the units you're supposed to have. I gave you Kelvin, liters, and atmospheres. Now you just solve for N. Okay. In number 7, you need to be careful because it's not balanced. Okay, so make sure you balance it. I balance it by putting a 4 here, so you have 4 NO3s, and I put a 2 here, so you have 4 LIs and 2 SO4s. So now I'm balanced. Now, use the mole map that I gave you on your cheat sheet. In that, you can go from grams of one thing to moles of it, then to moles of a new thing, and then into grams. So just follow the chart. So here, I'm given 250 grams of lithium sulfate. Okay. I first need to get into moles of lithium sulfate. That's the first step. So I'm going to put grams on bottom, moles up top, because the grams cancel. Now I'm in moles of Li2SO4. I'm not going to put numbers yet. I mean, they're there, but I would first put out the units. So moles of Li2SO4. On bottom, you'll put moles of Li2SO4. On top, you'll put moles of LiNO3. Okay. Last step is now to get into grams of LiNO3 because that's what it's asking you for, right? How many grams of lithium nitrate? So I'm going to put moles of LiNO3 on bottom and grams of LiNO3 up top. If you notice in the mole map, the number that you need to use for the gram to mole conversion is the molar mass. So this is the molar mass of Li2SO4. If you didn't get that, make sure you are multiplying the mass of lithium by 2, adding sulfur's mass, and then adding oxygen's mass times 4. Here, as you have on your cheat sheet, you need to use the coefficient. So the coefficient for LiNO3 is 4, for Li2SO4 is 2, and this is the molar mass of LiNO3. So at this point, guys, you should be being able to do these steps. It should be really easy, second nature. If you can't, please come in and work one through with me. In this problem, I'm going from molecules of water into liters of oxygen, and we're assuming I'm at STP, so I can use that 22.4 conversion. So molecules here, molecules on bottom, and then moles of H2O. Make sure you're putting H2O because some people get confused, okay? Sorry about that. So then here I'm in moles of H2O. Put moles of H2O on bottom, moles of O2 up top, moles of O2 on bottom, liters of O2 up top. Here I'm going to use Avogadro's number, so there's 6.02 times 10 to the 23rd molecules in 1 mole. Okay, this again is the coefficients because I balance my reaction. This is a combustion reaction, so CH's and then O's show for balancing. And then liters and moles is 22.4. Okay, I need 2 sig figs, so this is my final answer. Alright, this problem is almost identical, except I'm going to be going from grams to molecules. So if you notice, grams to moles, moles to moles, but it'll be moles of HCl. Okay, and now I need to get into molecules. So moles of HCl on bottom, molecules of HCl up top. Okay, so I've got 6.02 here. I've got the molar mass of BaCl2 here. This should not be too hard, I'm hoping. Okay, we're now getting into frequency and wavelength and everything like that. I need to be using this formula here. C is given to you, it's 3.0 times 10 to the 8th. Your wavelength is 0.53, and then that's frequency. So you just need to divide both sides by 0.53, and you get this answer. Be careful with your units. Frequency is seconds to the -1. Okay. For here, I give you the energy and ask for the wavelength, so this is going to be a 2-step problem. I first solve for frequency, which you can see here. Here's my energy, my Planck's constant, and my frequency. Okay, divide both sides by the 6.626. If you guys are not getting this answer, it's because you did not put this in parentheses when you divide it. Make sure whenever you have that multiplication sign that you are putting it in parentheses. Okay, so here's my frequency. Now I need to plug that into this formula to solve for my wavelength. So plug that in there. Your C is 3.0, and here's your answer. Okay. How are frequency and wavelength related to each other? They're inversely related. Now, something for you to know, energy, when energy increases, it becomes, if you think about like the waves that we've talked about, they become much more frequent. And so if you think about it, when energy goes up, so does frequency. So those are directly related, which means when we consider wavelength and energy, they're going to be inversely related. Okay? Because if you imagine, if you see a wave that looks like this, it has less energy than one that's going like this, right? And so one that's much more, one that has a shorter wavelength has higher energy, so they're inversely related. For here, it's asking for the frequency, but you have to notice I'm in centimeters. Okay, I give you the wavelength, you first have to convert to meters. Okay, because the units for C are meters per second. So you first got to convert. You can do this, I promise. There are 100 centimeters in a meter. You can do this conversion. Okay, and then you just plug in your wavelength and solve for frequency. So it's seconds to -1 for the units, and you need 2 sig figs. All right, 15, you can pause it to check your answers. I'm not going to go over all of these because this should be a review. The only thing for here, for these two, if you have a +2 charge, what that means is you lost 2 electrons. So Ca normally has a 4s2 here, but since it lost 2 electrons, you get rid of the 4s2. While for here, F-1, that means you gained 1 electron. F normally is 2p5, but since it gained an electron, it's now 2p6. Okay. All right. I then asked you to write the orbital diagram for MO. Okay. So remember, S, no matter what energy level, S's always have one orbital or one box. So I've got 1s2, 2s2 here. Remember, P's always have 3 boxes, so 2p6, 3s2, 3p6, 4s2. D's always have 5 orbitals and 10 electrons in them, so there's your 3D, there's your 4p. And then remember, this one's an exception. So right here you've got, it used to be 4d4, but it would rather be half filled and take 1 electron from the 5s. It's one of your exceptions. Any d4s and d9s are your exceptions. So you're going to remove 1, so it's just 1 in 5s, and then 5, so it's half filled in your 4d. Also, this is your shorthand electron configuration for MO. You've got to put KR in brackets and then 5s1, 45. If you don't remember how to do that, please come in. All right. For PBr3, I got 26 valence electrons, so you got this shape. This should be familiar at this point. This is pyramidal. Come in and make it if you don't see that. This is tetrahedral because you got 4 things sticking off, because with electron geometry, you consider the lone pair of electrons as another item that you're considering. So now you got 4, so it's tetrahedral. The bond is polar because if you look on either side of just one bond, if they're different elements, it's polar. So this is polar. The molecular polarity, it is polar because these are pulling but nothing's pulling up, so it's going to be polar, and therefore it's dipole-dipole. For NO3, to make this work, you've got to use 1 double bond, and if you have 3 different places where it could be located, that means you need 3 different drawings. Okay? This shape, make it if you don't see it, but this is trigonal planar. Since there aren't any lone pairs of electrons on the central atom, the electron geometry is the same. Since you have different elements on either side of the bond, it's polar. However, since that's pulling that way, and that way, the molecule is going to be nonpolar because it does not move. Therefore, it's LDF, intermolecular forces. Okay. For CS2, I would, if I made this and made everyone happy, I'd be using 20 valence electrons. So instead, I need to be using 2 double bonds. Okay. This is a linear shape. The electron geometry is the same. Elements on either side are different. So the bond is polar, but the molecule is nonpolar, so it's LDF. We base intermolecular forces on the molecule, not the bond. Okay. SCl2 is your typical bent structure. It's tetrahedral. Both are polar and dipole-dipole. If you're needing help with these guys, I can't take the time now, but please come in. Ooh, this is really blurry. I'm really sorry. Bad picture. All right, I'm going to be able to explain this pretty quickly anyways. How many orbitals does the P subshell have? P has 3 boxes, so it's 3. Sorry, this is so blurry. Each orbital fits 2, so 6 total for P. For D, it has 5 boxes. Each has 2, so that's 10. The lowest energy level that you can have a D in would be your 3, because it starts at 3D. For, I believe this says, hold on one sec. If it says P, guys, then it's 2. If it says S, then it's 1. Sorry, I can't read this. Okay. For your other stuff, for the next question, for 21, remember as you move down across the periodic table, atomic radius decreases. As you move down it, it increases. So N has the larger atomic radius because it's the lowest. Sorry, because it's the farthest to the left, right? Because F would be the smallest. Ionization energy, you've got B, A, L. Remember, as you move down, it decreases. So the farther down you are, the smaller you are. So B would have the larger. Just keep those in mind. It's kind of funky. Which atom has a smaller atomic radius? I got BE, okay, because you're comparing BE, MG, and CA. As you go down, it increases. What has a larger metallic character? That pattern is the same with atomic radius, so it's going to be zinc. Okay. For here, guys, I'm really, really sorry this is not showing. Al needs 3 dots because it has 3 valence electrons. Each of these BRs, I drew 3 because they each have 7, so they're only going to accept 1 valence electron. Al needs to give away all 3, so each of them will get 1. So the formula would be AlBr3. For here, STP conditions are 1 atmosphere and 0 degrees Celsius, or the same 101.3 kPa and 273. That's just simple conversions. And the last problem, guys, you start with 0.85 atmospheres. You're getting into millimeters of mercury, so 1 atmosphere on bottom, 760 up top, and I got 650 millimeters of mercury. And for this 1.85 atmospheres, you put atmospheres on bottom, kPa up top. This is 101.3, this is 1 atmosphere, and so I ended up getting 86 for my answer. Okay, and that's it. Study hard.